Okay, so in this video what we're going to do is we're going to look at a modified version of growth and decay. And so this is essentially what we refer to as the general case of this. So the general case is that for whatever, suppose that the rate of change of a quantity Q is proportional to the difference. Okay, so as in we've got some difference where it's proportional. So where B is some proportion of Q, okay? Then our derivative dq dt is equal to some constant of that function, okay? Like that. So where K is a constant of proportionality. So what that means is that then Q must be equal to B plus AE to decay T. Okay, and so this is our generalized form, and this is where A is the value of Q minus B at time 0. Okay, so what you should, where you'll be expecting this is, it's unlikely that the problem would ask you to actually prove something like this, but questions routinely ask to prove by substitution that some function satisfies some differential equation. So as in, we want to be able to show that this function here works for this differential equation here. Okay, and to establish the value of the constant in terms of the initial value. Okay, so what we're going to look at is we're going to look at two examples. In this case, we've got an example here about growth rate of a population, and we're also going to do one about some a particular type of example, I guess you could say. So in a certain town, a growth rate of population is given by dn dt is equal to this, where t is measured in years. So show that n is equal to 125 plus AE to the KT is a solution of this equation. Okay, so it's population growth. So what we've got is we've got dn dt equals to k lots of n minus 125. And we know that n is equal, we want to show that n is equal to 125, not n is equal to n, it'd be weird. We want to show that n is equal to 125 plus AE to the KT is a solution to this differential equation. So what we're going to do is if we substitute this into our n value here, we essentially should get a solution. So if n is equal to 125 plus AE to the KT, then dn dt must be equal to, so we scrap this and find the derivative of this, we get k AE to the KT. Now we want what we want to do is we also want to show that dn dt is equal to k lots of n minus 125. So this is going to be our right hand side, okay? Now what we're going to do is we're going to substitute into our left hand side. Oh, sorry, this is our left hand side. Jeez, can't even tell my left from my right. So that's our left hand side. We want to show that that's equal to the right hand side. So the right hand side is k n minus 125, okay? So if we substitute n into this, we get k lots of 125 plus AE to the KT minus 125. So this is right hand side is equal to this, which is equal to that, which is equal to, well, by doing some cancelling, we get 125 and 125 there, and we're left with k lots of AE to the KT, which is equal to the left hand side. Okay, so the right hand side is equal to the left hand side, just like that. So all we had to do was just find the derivative and then substitute that value into the other term, or the other form, to just show that that was the case. So that's part A. Part B says, if the population is initially 25,650 and after 5 years it is 31,100, find the population after 8 years, okay? So, the initial value, so we're going to go n is equal to 125, and this is for part B, n is equal to 125 plus a e to the kt, like that. Okay, and we want to show that this, we want to find t of 8. Now, with t of 8, we also know that initially, so when t is equal to 0, so at t is equal to 0, just give me 1 second, I'll put it up on my screen so I can actually not have to keep going up. So t is equal to 0, n is equal to 25650, and at t is equal to 5, n is equal to 31100. Okay, so what this value will do here, or these values will do here, is will help us find our value for a. So this will help us find a, and these values here are going to help us find the value of k. So up in here, so our k and our a values, so that we can then use that formula to find what t is. So at time 0, so at t is equal to 0, we've got 25650 is equal to 125 plus a e to the 0k. So the 0k is going to give us 0. So it's 0 up here. So that's going to cancel that out. And we're going to be left with 25650 is equal to 125 plus a. So a must be equal to 25,500 by subtracting 125 from both sides. Okay, so that's the a value. So now that means our formula is going to become n is equal to 125 plus 25500 e to the kt. So now what we need to do is we need to find, well, what's that value of k? What's the constant of proportionality for this exponential? So at t is equal to 5 is our next step. So at t is equal to 5, we're going to substitute those values in that we know. So 31100 is equal to 125 plus 2,550, or 25,500, I should say, e to the, now it's at 5, so 5t. Okay, so what we're going to do first is we're going to subtract 125 from both sides to get, I think it's 29,975, and that's equal to 25500 e to the 5t. Now we're going to divide both sides by 25500. And that's going to leave us with, and we're just going to leave this in exact form for now. So 25500 equals to e to the 5t. Now we want to isolate that 5t, so we're going to take the natural logarithms of both sides. So 29975 over 25500, and that's equal to the natural log of e to the 5t. So that's going to give us that log of 299775, and that's the wrong color. 75 over 25500 is equal to 5t, and so that t must be then equal to this over this over 5. So t in this case must be equal to, so putting it into our calculator, so 29975 over 25500 all over 5, which gives us t is equal to 0.03. Okay. Sorry, not t, k. Jeez, what am I doing? This should be k, not t. Because our t is equal to 5, not our k, our t. Sorry, not our t, our k. So k, k, k. That's my bad. K, k, k. Another k, and another k. So our constant of proportionality in this case is k is equal to 0.03. To 2 decimal places will do. Actually, no, it says 3 significant figures. So in this case, it's going to be Oh, no, it doesn't say actually. So I'll just leave it at that. So 0.03. So that means now in this formula here, we can substitute our new values in. So we've got n is equal to 125 plus 25500 e to the 0.03 t. So this is the formula in its whole entirety for this specific situation. So now what we can do is we can actually find what the population is after 8 years. So for t is equal to 8, now we get n is equal to 125 plus 25,500 e to the 0.03 lots of 8. So n is equal to 125 plus 25,500 to the power of 0.03 times 8. And we get the population is 136. Oh, I forgot the E. Jeez. No wonder that was looking very odd. Shift A. Whoops, that didn't work. For God's sakes, calculators can be annoying sometimes. So 2500 e to the 0.03 times 8. That should be a bit better. There we go. So after 8 years, it is equal to 32,541. And because it's a population, our answer is 0.85, so we're just going to leave it to a whole number because we can't particularly have 0.85 of a person. And we don't need to round it up because we quite haven't made it to that one extra person yet. So it's always an approximate amount in that case. So that's part B. So it's a lot of working out for just one part, but we had to find the A and the K before we could find out what the value for E was. So it's a bit of work, but we get there in the end. After how many years to 3 significant figures will the population reach 4,000 or 40,000? So part C. Okay, so part C. So we want the population, so the n to be equal to 40,000. And we've got our formula, n is equal to 125 plus 2500 e to the 0.03 t. So in this question, we're trying to find what is t. So we're going to substitute our 40,000 in. Is equal to 125 plus 25,500 e to the 0.03 t. So it's going to be something similar to what we've done already. So subtract 125. So 40,000 minus 125 equals 39875, which is equal to 25500 e to 0.03 t. Okay, dividing both sides by 25500, so we get 39875. And we're just going to leave this in the exact form again. E to the 0.03 t. Okay, to get rid of log, we're going to, to the exponential, we're going to take logs of both sides. Okay, over 25500, and that's going to be equal to 0.03 t, as we know. So in this case, t must be equal to the log of 39875 over 25500 all over 0.03. So t must be, putting it into this, we get log of 39875 over 25500 all over 0.03. So the time when the population will reach this is 14.9 years. Now, we can have a decimal for time because time is, it's a continuous variable, whereas a population is not, it's only discrete numbers. So 14.9 years can definitely pass because it just means 14 years has passed and almost the 15th year has passed before it hits that number. Okay, so find part D. Part D says find the rate of growth of the population after 8 years. So the rate of growth is dndp. So dndp. dp dt. Jeez. So it's number of people with respect to time. So in part A of this question, we've actually worked out the formula for the derivative, or it told us at least anyway, which was k lots of ae to the kt. So k lots of ae to the kt. So you could have just taken the formula from up here and substituted and just found the derivative of that. But what we can do is we can using k is equal to 0.03 and t, sorry, not t, and not k either. A is what I want, and A is equal to 25,500. So dn dt is equal to 0.03 times 25500 e to the 0.03 t. So then at time is equal to 8 for 8 years. Okay, the rate, so dn dt is equal to 0.03 times 25500 e to the 0.03 times 8. So dn dt is equal to so 0.03 times 25500 e to the 0.03 times 8. So it's increasing at 972.5 per year. So again, with this one, we could include the 0.5 with this one because it's a rate, and the rate's not having to be an exact amount. But I will also want to bring your attention to the fact that if you have a look at the derivative is just the original function times by the k value. So if you already have your value for 8 years, so our 8 years one was this value here, so 32541. 3541. What you could do is you could also times that 0.03, and that should give you very, very close, because this one is rounded, but very, very close to what our original amount was. Okay, so alternative method is k lots of n. Okay, so in this case it's k times, or 0.03 right at t is equal to 8. So it's 0.03 times, and I think our value was 32541. So that is equal to, it's up on my screen, 976.23. Like that. So that's the alternative method. Okay, now part E says sketch the graph of population against time. Okay, so the graph of population against time. Now, this is not going to be a super good sketch. It is expected that you guys do much better sketches than what I'm about to do, but I'm just going to do one very, very quickly to show you a few things. So the first thing I want to show you is that, well, we can work out what the initial starting time is by going to t is equal to 0. So it's at 25500. So let's say we go up by 10,000s. So 10,000, 20,000, 30,000, 40,000, and 50,000. Okay. So our initial starting value is about 25,500. So that's about here. Okay. So if I go 1, 2, 3, we'll go up to 8 for this one. 5, 6, 7, and 8. Okay, so 25,500. We can also work out what our 8th value is. So our 8th value in this case is at t is equal to 8 was 32,541, so 32. So at 8 years, it's about here. Okay, and so that means our exponent, because it's an exponential growth, it's going to be growing at a rate like that. I think I might actually, I might actually change my scale a bit. for this one because that seems very, very low. So let's go 10,000, 20,000. Oh, no, that's too... Nah. I've stuffed it now. Okay, get rid of those. Get rid of there. I want black. Thank you. Okay, so 10, 20, and 30,000. Okay, so the initial starting was 25,650. So about here. Okay, at time is equal to 0. And 31,000 at 5 years. So 5 years was about 31,000. So about here. And 8 years was about here. So it's going to be a growth that's starting to look like something similar to that. So it should be sort of like it should start growing up like that, really, because it's an exponential growth and it's going to start. Like the idea is that it goes in that sort of direction. So we're sort of like focusing on this part. Okay, with that being said, that's the end of that example. Now we're going to do the other example all in this one video because it is just another application of this, and it's an application of, it's an application of the exponentials, but using a formula or an idea. Coming from physics, which is Newton's law of cooling. Now, Newton's law of cooling is a well-known example of exponential decay. So think of when a hot object is placed in a cool environment, and then the rate at which the temperature decreases is proportional to the difference between the temperature of the object and the temperature of the environment. So, as in, it's never going to possibly get below the environment that it's in, but it will get pretty close to it, or to it exactly. So we're thinking decay this time. So the decay formula is, and I'll just write it here really quick, is dt, so the temperature with respect to time is equal to minus k of t minus the environment. So the temperature outside minus the environment temperature, where k is a constant of proportionality. So again, it's very similar differential equation to what we had before. Okay, but dt, so the derivative of the temperature with respect to time. So that's why it's a capital T and a lowercase t. And so this law also applies to a cold body placed inside a warmer environment. However, the cold body would increase. So it'd be an exponential, probably not exponential growth, but it'd be like the opposite, where it gets closer to the warmer temperature, and then vice versa. Okay, so a saucepan of water is heated to 95 degrees Celsius. The room temperature is at a constant 23 degrees. Okay? And the water cools down to 55 degrees after 5 minutes. The cooling rate is proportional to the difference between the water and the room temperatures. So show that the equation of the water temperature is T is equal to 23 plus 72e to the negative 0.61162 T. So what that means is, what we're going to find is we're going to be using T is equal to 125, well, it's going to be, it's going to be E plus AE to the KT, okay, is what we're going to be using for this one, because we're going to be trying to find the form of the exponential growth, okay, where we know the environmental amount, or if you will, is the environmental temperature, I should say, is a constant 23 degrees. So that's going to be, so E is equal to 23 degrees. So it's going to be T is equal to 23 plus AE to the KT. So we need A and we need K, just like we did before. So what we're going to do is we are going to use the fact that it cools down to 55 degrees after 5 minutes, okay, and that the initial amount is 95 degrees Celsius. So at T is equal to 0, capital T is equal to 95 degrees, and so this is going to help us find A, and at T is equal to, I think it's at 5 minutes, so they like the fives. 5, the capital T is equal to, and I think it was 55 degrees. So 55 degrees, and this is going to help us find T. K. Okay. So at T is equal to 0, we've got the temperature is equal to E to the E plus, oh, sorry, not E, because we know what that E value is. It's the 23 degrees. So the environmental, so 23 plus AE to the KT. Okay. Sorry, just give me one sec. So 23 plus AE to the KT. Yep, so AE to the KT. Okay, and we know that the initial temperature is, oh, I got it here, so it's 95 degrees is equal to 23 plus AE to the, and it's at time 0, so it's 0K. Okay, so dividing both sides by 23, we get 95 over 23 is equal to AE to the 0K. Now the 0K is just going to cancel out, and that's going to leave us with A. So A in this case is equal to, and this one should be equal to, it should be equal to 72. Why is that? Oh, because it's not plus. It's, sorry, it's not divide, it's a minus. So it's 95 minus 23. So A should be equal to 72 degrees. Okay. So that means our formula is going to become T is equal to 23 degrees plus 72 E to the KT. So at this point. So now at T is equal to 5. So it's only minutes this time. So T is equal to 5. Now capital T is equal to 55 degrees. Okay. So substituting it into this formula up here, we get 55 is equal to 23 plus 72 E to the 5T. Now remember, we're trying to find that little value of T. So I'm going to go 55 minus 23 is equal to 72 E to the 5T. So that means that we're going to get, K, not T, sorry, because the K is, did the same thing last time. The K is the value we're trying to find because the T is equal to 5. So 55 minus 23, which is equal to 32. That's equal to 72 E to the 5K. Okay, divide both sides by 72. We get 32 over 72 is equal to E to the 5K. Okay, taking logs of both sides, we get log of 32 over 72 is equal to log of E to the 5K. And we know that that's just equal to 5K. So to work out the K, we're going to divide both sides by 5, and we're going to get log of 32 on 72 all over 5. So putting that in, log of 32 over 72 all over 5. And we should get negative 0.16, which I'm hoping is the value up there, or negative 0.162. So K is equal to negative 0.162, not T, 2. So therefore, T is equal to 23, I believe it was 23, yep, plus 72 E to the negative 0.162. I keep wanting to do a T instead of a 2, T. Okay, there we go. So there's our formula for this. So that was part A, which was that bit there. Now find the temperature of the water after 30 minutes. So nice and easy for B. At T is equal to 30, we're just going to find what capital T is. So 23 plus 72E to the negative 0.16 times 30. So T is, and this is just a matter of substituting it straight in. So 23 plus 72 E to the negative 0.16 times 30. That's equal to 23.59 degrees. So that's how much it should be. So notice how it's not below 23, but it's getting really close. Because after 30 minutes, if you think about something, it's going to get pretty cold. And it's never going to be colder than the area it's in, but it's still pretty chilly. Okay, part C now. So part C says, when will the water temperature reach 30 degrees? So when will it reach 30 degrees? So it's going to be before 30 minutes, because 30 minutes is 23. So what we're trying to do is find when is capital T equal to 30 degrees. So you get 30 is equal to 23 plus 72e to negative 0.16 t. Okay, subtract 23 from both sides. I'm going to get 7 is equal to 72e minus 0.16 t. Okay, divide both sides by 72. We're going to get 7 over 72 is equal to e to negative 0.16 t. Take natural logarithms of both sides. I'm going to get log of 7 over 72 is equal to negative 0.16 t. Okay, and then dividing both sides by negative 0.16 should give us t is equal to log of 7 over 72 divided by negative 0.16. Okay, so putting that one into our calculator, we're going to get, so it's, I want shift, I want log of 7 on 72 all over, or divided by negative 0.16. And there you go. So at time is equal to 14.56, or 57, I should say, minutes is when that will happen. Show that temperature of the water approaches 23 degrees as T approaches infinity. Okay, so quite simply, as T approaches infinity, so let's let T be equal to a very big number. Okay, so this is part D. Because we can't actually work out what infinity is, we can see what happens when T gets very, very big. So let's say N is, not N, in this case it's capital T, isn't it? So T is equal to, so it's 23 plus 72 e to the negative 0.16 t. Okay, so as T approaches infinity, okay, so let's put it on. So it's 23 plus 72 e to the, let's say at T is equal to 100. So it's not a super big number, but it is a big number nonetheless. Okay, we get, T is equal to 23.000081. Okay, at T is equal to, well, let's just add a 0 on 1,000, and that's going to give us essentially T is equal to 23. So once the number gets big enough, when we get to 23 like that. Okay, so with that being said, that's pretty much the end of this video. So exponentials, like, it's just a matter of practicing it to get them, okay? So if you just practice them over and over, it's just very, very procedural, okay? So if you just keep practicing, there's nothing too tricky about them. It's just plug it into a formula and do some algebraic manipulation. Okay, with that being said, that's going to be the end of this, and it's going to be the end of that topic as well. And I will talk to you guys in the next one. Make sure you hit like, subscribe, and leave a comment below. Ciao!